And we are live. Welcome back to our fractions unit. Okay, I am Doug, of course, and I'm still Doug. And Mocha's still here. Come here, Mocha. I'm going to introduce Mocha, and then I'm going to banish her from the room. So Mocha, who is not very good at multiplying fractions, look at the camera, please. Okay, she has no idea that a camera exists, even though it's right there. Look, she's sniffing it. She still doesn't realize it's there. Okay, so I have introduced Mocha. Soon I will banish her upstairs because I do not want her to start barking if someone comes to the door. And we're ready to get into fractions. What's this week's shirt? This is a special one, actually. This is the GAA, Gaelic Athletic Association. It's sports in Ireland. I bought the shirt when I was in Ireland. And it covers sports of hurling and Gaelic football, which are special sports that are usually only played in Ireland. Kind of cool. I only have a couple of these shirts. Now let's get into the fractions. We're going to be mostly doing a lot of stuff that has to do with multiplying fractions today, but that's really a big topic. It's actually easy and students like it, which is good. But it's also a big topic in the sense that once you learn how to multiply fractions, it keeps coming back and it keeps on being useful in so many different ways in math, which is also good. Once you get good at something and you know you're going to use it again and again, that means that the time you spent working on it was very well spent. I'm just going to run over and get Mocha through the staircase so that she can't interrupt us. And then I'll be back, and I apologize for leaving you with just this lovely fractions label to look at for the next few seconds. Okay, go. Be free, Mocha. And I'm back. Where are my notes? Here's my notes. Page 1, page 2, page 3. That's good. And where is my chalk? Here is my chalk. Let's get into it. We're going to start multiplying fractions right away. Okay, how do you multiply fractions? Well, I guess we should talk about that. I'm going to put a pair of fractions up and multiply them as an example. How about 1/4 times 1/2? Well, the good news is, one of the reasons that we teach multiplying first before division, addition, and subtraction is because it's easy. And that's good news. So how do you multiply fractions? Well, we know what numerators are. We know what denominators are. When we multiply fractions, we multiply the numerators and we multiply the denominators. It is rather straightforward. So our answer will be a fraction. And I'm going to start by multiplying the numerators. 1 times 1 equals 1. And now the denominators. 4 times 2 equals 8. I have my answer. My answer is in the form of a fraction. Sometimes I can simplify it. Sometimes I'll do other steps afterwards. But right here, there's not really much extra to do. 1/8 is a perfectly good fraction. It's very simplified already. And it's the answer to 1/4 times 1/2. So that wasn't hard, was it? I knew that you would not think it was hard. But what I want to do is slow down and look at this a little bit more carefully for a bit. First of all, the word of. In math, one of the things that's really useful to learn is the word of often means multiplication. And once you know that, it makes it easier when you get to the type of math where there are word problems, where there's English language instructions, and they're giving you hints about what to do. When you see the word of, often that's a bit of a hint that multiplication might be useful. It's not the only way we use the word of in word problems, but it is a useful hint. It's something to consider. So let's think of this question and rephrase it like that. 1/4 of 1/2. So yeah, multiplying fractions is an example of one of those times when of means multiply. How does that make sense? Pizza. Pizza are, of course, always useful for fractions. So what I'm going to do is I'm going to draw a couple of fraction pizzas. So first I'll draw this pizza. And because it's going to represent 1/4, I'm going to make it one of those pizzas that you cut into 4 pieces. So I'll do that. And I may as well show the fraction with my shading. There's 1/4 of a pizza. 3 of the 4 slices have been taken away, but there's still one left. We have 1/4 of a pizza. We already know that. And then 1/2 of a pizza. Well, if I use a pizza that's the same size, but instead of cutting it into 4 equal pieces, I cut it into a half, well, it looks like this. So there's 1/4 and a half. What's 1/4 of a half? Oh, okay. So that's like, kind of like a different question. If we multiply 1/4 by a half, we get 1/8. We know that. So I'm going to draw the 1/8 pizza. That equal sign is too small. There. I'm going to draw the 1/8 pizza. So I'm going to divide this one into 8 equal slices. And I'm going to shade just one of them. How does this make sense? How can I make this make sense? Well, if we had half a pizza, I'll draw it up here. There's that half a pizza again. Drawn a little sloppy. But let's say we started with half a pizza. That doesn't happen very often. Usually pizzas come as intact circular pizzas. But let's say you started with half a pizza for some reason. I went to the fridge one day and looking for something for lunch and realized, oh, there's half a pizza left in the fridge. Okay, so I have half pizza. That's a pretty good starting point. I can manage to get some lunch out of this. But what if I get a message from my wife Bunny and she says, okay, make sure that you only ate 1/4 of the pizza that's left in the fridge because I promised the rest of it to the grandkids. Oh, okay, so I can't eat the whole half pizza. I can't eat half a pizza, but I can have 1/4 of the pizza that's left. So what is 1/4 of half a pizza? Well, I would divide the half pizza into 4 equal slices. So I'll do that by drawing really thick lines so we can see them. There's my half pizza that's cut into 4 equal pieces, and I'm only able to eat 1/4 of it. So therefore, this is the amount that I'm going to be able to eat, the really, really shaded amount. 1/4 of half a pizza is this one slice, which looks kind of like this slice. It's 1/8 of a pizza. So pizza, as usual, works really well whenever we're learning anything about fractions. Pizza is useful for a lot of math, but it's really useful for fractions. So I'm not going to draw a lot of pizzas in this week's lesson. We've moved on from the pizzas. And as usual, this is making me hungry. I'm starting to drool a little bit. Okay, but the idea that of means multiplication in this situation is really well illustrated by Doug's pretend situation where there was half a pizza in the fridge and Bunny said he could only eat 1/4 of the pizza that was left. And how much is that? Doug successfully realized, because he knows how to multiply fractions, that he was allowed to eat 1/8 of the pizza and he didn't get in trouble with Bunny. So that's good. Math is useful in real life. Math is useful with real pizza. Pizzas are very useful in real life. Math, pizza, life, it all goes together so well. I'm just keeping an eye on the time when I lean forward like this because I know how much time I want to spend on each of the topics in this week's lesson. Okay, so the next thing I want to do is I want to practice this a lot. And I'm going to practice it without pizzas because that will make me able to practice it more quickly. So first I will erase. Goodbye pizza. Feel sad to say goodbye to the pizza. I really do like pizza. And I have said to some of my math students in some of these videos that sometimes when we get pizza I eat as many as 6 slices. Well, that wasn't true. It was because I was doing a statistics question and I wanted to have some variety in the answers, so sometimes Doug would have 6 slices and sometimes 5 and sometimes 4. I'm going to confess, the last time that we ordered pizza, I only had 2 slices. I'm learning some self-control when it comes to pizza. Okay, so another multiplication problem, and I don't want it to be too tough. I want to choose something pretty easy. We already started with one that had a 1 in the numerator, the first fraction, and a 1 in the numerator of the second fraction, so we know we're going to do 1 times 1 equals 1, but I'm going to do that again, but this time I'm going to use 1/3 and 1/5. We're going to multiply 1/3 and 1/5. How do we do that? We know what to do. Numerator times numerator is 1 times 1. Our new numerator and our answer is 1. Denominator times denominator is 3 times 5, and that is 15. Isn't it amazing how useful it is to know your multiplication tables really well when you're doing this sort of math? We can focus on the fractions and not have to worry too hard about the multiplication because we have been practicing. 1/15 is the answer. It's correct. I'll do another one, but now let's start making it at least slightly more challenging by not always having ones in my numerators. How about 2/3 times 3/4? I did this style of 3 here and that style of 3 there. That's not very consistent, but those are both 3's. Okay, numerator times numerator. It's not ones this time. 2 times 3 equals 6. And 3 times 4 equals 12. So we have 6/12 as our answer. Can we simplify this? Yes. But are we going to do it now? No, because I'm going to do that later in the lesson. 6/12 is not a fully simplified fraction, but it's still a fraction. And it's actually a really good answer. And if you had a pizza that was divided into 12 equal slices, well then you don't. Okay, we know what would happen with the pizza. Doug would eat it, but he wouldn't eat all 6 slices. Not at least the right way. Okay, so let's do another one. This is fun. Multiplying fractions is fun. It's one of those many types of math that I like a lot because it feels like a puzzle. And I could just sit there doing that puzzle all day. I actually enjoy it. I hope the students agree. So let's do a few more to make sure that we're getting plenty of exposure to this, to make sure that we're feeling like this whole thing is easy. There's more to it, of course, but the idea, the basic idea is you multiply the numerators, and that gives you your new numerator. It's hard to say new numerator. And then you multiply the denominators, and that gives you your new denominator, which is not so hard to say. We can learn this, we can remember this forever if we practice it enough right now. So let's do another one. How about 1/2 times 8/9. Okay, what's so scary about this? Simply I have one fraction with really small numbers and another fraction with bigger numbers, but that's nothing to be scared of because these are multiplications of 1 by 8 and 2 by 9, which are actually kind of near the beginning of our multiplication table, so we probably find them easy. 1 times 8 equals 8. And 2 times 9 equals 18. And I have another answer, and it is a correct answer. 8/18 is the answer. Can I reduce it? Yes. Will I reduce it right now? No. Okay, another one. What can we do to make this interesting? How about trying some larger numbers, but still staying with multiplications that are part of the multiplication table? How about 11/12 times 4/7? Looks crazy hard, doesn't it? But is it? No, because we break it into pieces. If we had to do all of this at once, it would be scary. But we don't. We are just on numerator times numerator to start with. We don't really have to think about the denominators at first. That's one of the things that makes this process not so bad after all. 11 times 4, that's an easy one, 44. 12 times 7. Some people take a little longer to learn that in their multiplication tables, but it is 84. We have another fraction that could be reduced, but it's still a perfectly good fraction when it's in its non-reduced form, 44/84. And we get a reminder that no matter how big the numbers get, we know the words to use. Because if we can count to 84, if we can say 84, then we can say 84ths. And then that gives us the language we need to express this rather large-looking, complicated-looking fraction. Okay. Let's move on to a couple more examples. How am I doing for time? I'm doing fine for time. I want to do some more examples. I'm going to double check what the next topic is. And we're fine. Okay. So, what can I do to make this have a bit of variety? How about putting really big numbers in, but trying to choose really big numbers that aren't that hard to deal with? So 3/8, one of my favorite fractions because it happens so often in carpentry, which is my hobby, times 100 over 110. Okay, that looks crazy hard. These numbers are way bigger than you get when you deal with the multiplication tables, but 100 is kind of a round number. Multiplying by hundreds actually is easier than some of the smaller multiplications that happen in the multiplication table because multiplying by 100 you get the answers so quickly. 3 times 100 is 300. I think most of the students will answer that really quickly and be surprised themselves with how quickly they can answer it. 8 times 110 is a little bit more challenging, but it's kind of like 8 times 11. And 8 times 11 is kind of easy because it's 88. The double number kind of helps. 8 times 110 is going to be the same 88, but there's going to be a 0 in the answer. So 880. Wow, 300 over 880. A crazy big fraction with crazy big numbers, but can we do it? Yes, because we're just doing the same process we were already doing. Are we afraid of a big fraction like that? No. Can we reduce this fraction? Yes. Will we do it right now? No, I'm still not doing that. Okay, let's do another one. I could have put another example right underneath this one, but I was already walking over to my eraser cloth, so I may as well erase. Okay, anything else? How about if I try and take some of the more challenging multiplications from the multiplication tables and do that in both the numerator and the denominator? So I'm trying to make this hard. So how about 7/9 times 6/8? Okay, so as I always say when I do work on the multiplication tables, there are some of the answers in the middle of that table that you kind of learn last. And 7 times 6 is one of the ones that comes along a little more slowly. 7 times 6, though, is 42. And 9 times 8, that's one of the last ones a lot of people learn. 9 times 8 is 72. 42 70-seconds. I don't want to say 42 72ths. So 42 70-seconds is a perfectly reasonable answer for a question like this. This is starting to feel like it's too easy. I wonder if the students think it's feeling too easy. What can we do to stretch our math brains a little bit more? What extra stuff happens? Looking at the time again. Okay, so let's throw a kind of a curveball at us. We will try when we include 0 in the fraction. Now, you don't see zeros in fractions very often. When you have 0 as a number, you don't really have to express it as a fraction, but of course you can. And I know that we talked about that last week. So what if we have 0 over 5 times 2 over 3? Okay, we're doing the same thing. 0 times 2 is 0. And 5 times 3 is 15. Now, as soon as I see 0 in a numerator, I know that the answer is actually 0, because 0/15 is equal to 0. And I can do this. And if I want, I can skip right to the answer, but I like it better when people show their steps, because especially when you're just learning something. So a 0 being in a numerator is not a problem. We're not going to do any of these with the 0 in the denominator. I don't want to go there. But a 0 in the numerator is nothing to be afraid of. It just means that when you multiply your numerators, you're going to get 0 as the numerator of the answer. And then you can simplify it very quickly by saying, oh, okay, 0/15 is equal to 0. Why? Well, if you had a pizza that was cut into 15 slices, but there were 0 left, it means you have 0 pizza. That's why. So you can say, I have 0/15 of the pizza. You may as well just say, I have 0 pizza. I have no pizza. 0/15 is equal to 0. 0 over 1 is equal to 0. 0 over 12 is equal to 0. 0 over 10,000 is equal to 0. So it's another one of those things in math that sounds like it might be hard, and it turns out that it's not hard. Once you get it with the smaller ones, you can apply the same thing to the bigger ones, and you realize that you can do those too. So that's interesting. What other interesting things can happen? Looking at the time. I think I want to do a bunch of examples of my next one. Okay. I think we need a lot of examples of this. Now, we may have heard of the improper fraction. I know that I mentioned it last week, but I didn't get into it very much because it was such an intro to fractions lesson. I didn't want to introduce anything too crazy. But an improper fraction, it sounds bad, but it's not bad. An improper fraction is actually a good thing. I like improper fraction. It's one of those ones where the numerator is bigger than the denominator. So how about 4/3? So if this was pizza, if this were pizza, let's get the grammar correct. 4/3 of a pizza means that my pizza has to be divided into thirds, which I didn't draw that well. But I don't have 4/3, so 4/3 of the pizza means I have more than one pizza. So if I take 2 pizzas and divide them both into thirds, And now I shade, okay, so 4/3 of a pizza means I have a whole pizza, and then I need a fourth piece, so that's how much pizza I have. I have one pizza plus 1/3 of a pizza. I have 1 1/3 pizza. 4/3 can be expressed as 1 1/3. This is converting between an improper fraction and a mixed number. Mixed numbers are useful sometimes. Improper fractions are useful a lot of the time. I actually find improper fractions more useful more often when I do my math. But this is a good situation for where a mixed number is useful. Because saying I have 4/3 pizzas, people might not really feel very sure what you're talking about. But when you say I have 1 1/3 pizza, people can visualize this. And so 1 1/3 can be a little bit more graceful sometimes than 4/3. But they mean the same thing. It's really the same number. I'm not going to do too much with these mixed numbers in this lesson. I'm going to stick with the improper fractions. So I'm going to erase this and these pizzas. And I'm going to do a multiplication where there's, oh, this piece of chalk is no longer viable. Where there is an improper fraction as part of a multiplication. Is this going to cause all sorts of big complications? Well, actually, no, because the process is going to be the same. So let's do a multiplication where one of the fractions, the first one, is an improper fraction. The numerator is bigger than the denominator. The second one, I'll go back to the usual. I'll make this one 2/3. So both of our denominators happen to be 3, but that's fine. We know all we're doing is multiplying the denominators, but first we're going to multiply the numerators. 4 times 2 is 8. 3 times 3 is 9. 8/9 is my answer. There is nothing wrong with that. Why would it be a problem that one of the fractions has a numerator bigger than the denominator? Well, it isn't a problem. So I don't want the students to think it's a problem. Let's do another one. I won't erase that one yet. Let's do one where the second fraction has an improper fraction, a numerator bigger than the denominator. So how about 2/5 times 7/4. There, 7's quite a bit bigger than 4. Okay, can we do this? Yes, we're doing the same process. The process has not changed. 2 times 7 is my numerator is being multiplied, and it gives me 14. And 5 times 4 is the denominators, and that's giving me my denominator and my answer, 20. 14 over 20, 14/20 is my answer. Nothing wrong with that. Let's do a couple more examples, though. This time, we had the first one, numerator is bigger than the denominator. Here we had the second one, numerator is bigger than the denominator. Let's do one more of each, where the first one has the numerator bigger than the denominator in one example, and the second one has the numerator bigger than the denominator in the second fraction. It's getting hard to say this because those words, numerator and denominator, are so long. I'm saying them so many times in such a short period of time. It starts to get to be a little bit of a tongue twister. I think I'm still pronouncing them correctly. Okay, so how about 6/5 times 1/10? And so this is the one where the numerator is bigger. But let's also do 9/10 times 2/7. Is anything going to change? Have I really created anything new for us? Well, let's find out by answering it. 6 times 1 is 6. 5 times 10 is 50. 6/50 is the answer. It's a perfectly reasonable answer. 9 times 2 is 18. 10 times 7 is 70. Again, there's nothing new really here. The fact that sometimes I have, I made a mistake. Okay, I'm just going to do a third example. So here's my example where the numerator is bigger than the denominator. Here's my example where the numerator is bigger than the denominator. So I'm just taking this one and I'm turning it upside down because I accidentally didn't do an example of what I was trying to do. This is still a perfectly good multiplication problem, so I'm not going to remove it. 9 times 7 is 63. 10 times 2 is 20. I have 63/20, which sounds like a kind of a weird fraction, but it's a fraction. And there's nothing wrong with it, and it's the right answer. But has anything new happened now? Yes, one new thing happened. The answer this time has a numerator that's bigger than the denominator. Why? Why did the answer of this one end up with the numerator so much smaller than the denominator, and the answer of this one, it's the other way around. The denominator is way smaller. Well, the answer is in the numbers. 6 times 1 gives a really small answer because one of the values I'm multiplying is 1. 5 times 10 gives a pretty big answer because 10 is a pretty big number. Down here, 9 times 7 gives 63 because 9 and 7 are both pretty big numerators, and 10 times 2, well, 10's fairly big, but 2's small. So this becomes fun. This becomes part of the fun. The students can play around with the numbers and their fractions when they're multiplying and experiment with things like this. I managed to make the answer have an improper fraction. The answer has a numerator bigger than the denominator. Let's see if I can do it again. Let's make one where the answer's numerator is way bigger than the denominator. How are we going to do that? I think we already have an insight into how we're going to do that. So we want an improper fraction where the numerator is way bigger. So how about 12 over 5? Okay, so numerator is way bigger. And then another one, how about 11 over 4? I'm making it happen. I choose 2 really quite large numerators and 2 really quite small denominators. I know what's going to happen. 12 times 11, oh, that's from the multiplication table. How much is that again? It's one of the last ones that I felt really comfortable with. 12 times 11 is 132. 5 times 4 is 20. So yeah, it happened. Our numerator is way bigger than the denominator this time, and we have nothing to be afraid of. It's just another multiplication of fractions. In fact, it's starting to feel kind of routine. I'm starting to wonder whether I should even bother noticing whether I have numerators bigger than denominators in my question. And I'm realizing, well, if I didn't notice, it wouldn't really matter. I just would go ahead and multiply the tops and multiply the bottoms, and I'd get my answer, and the answer's right. So nothing wrong here. How am I doing for time? I'm doing pretty good for time. I'm quite happy. Okay, let's do another special case. This is the one. I'm still on my first page of my notes, but I'm running out of stuff from the first page of my notes. I'll erase this. And remember, when you're doing a lesson and it's getting long like this, we're already almost at half an hour. Remember to breathe every now and then. I have a tendency to forget that. You can tell by the way I'm talking that I'm getting to be a little breathless because I'm going on and on and on and on and on, and I'm hardly stopping. It's good to stop and rest sometimes, and it's good for the students. Even if the teacher is doing most of the yakking, the students need to take a breath sometimes. So you stretch. And you breathe a little slowly. And if you need a sip of water, you get one. And this is all just me leading up to the fact that I'm going to leave the camera again because I want a sip of water, and my water's over there. It's about 15 feet that way. But let's see. First, I'm going to put a problem up so that while students are waiting for me to come back with my water, they can work on the problem. So how about 5/4, oh, there's an improper fraction, times 4/5. I'll even put the equal sign and the fraction bar so we're ready to answer this, and I will not be gone for long. And this is pink grapefruit flavored sparkling water. Water is the important part, but I like the sparkling. It makes me feel refreshed, like soda pop, but without all the calories. Okay, so that's Doug having his breather and clearing his throat, clearing the chalk dust and all the conversation out of his mouth. Okay, so let's go ahead and do our process. 5 times 4 is, of course, 20. And now we will multiply the denominators. 4 times 5 is, of course, 20. So we have our answer. It's a fraction, and it's 20/20th. What? Oh, I'm acting surprised. I'm not surprised. Okay, so what happened here? what happened is I'm introducing the concept of the inverse fraction. It's just a word that we use in math. When you have two fractions where one of them is the same as the other except that it's upside down. Maybe I should just say inverse. Okay, the inverse of 5/4 is 4/5. It's the same fraction but upside down. And when you multiply two fractions that are the inverse of each other, well, this is going to happen. Because 5 times 4 is 20, but we also know 4 times 5 is 20. When you multiply, it doesn't matter which of the two numbers you put first. We've gone over that before, actually. So we end up with 20/20ths. We end up with a fraction where the numerator is equal to the denominator. Is this anything to be scared of? No. Remember when we had 0 as our numerator? We were able to simplify it very quickly by saying, oh, anything with 0 in the numerator is just equal to 0. You don't have to write it as a fraction anymore. Well, anything where the numerator and the denominator are equal to each other is equal to 1. So this could be seen as sort of a clever form of 1. If I wanted to write the number 1, but I felt like being really creative, I could write 20/20ths. It might sound like a bit of a show-offy thing to do, but it's actually a useful thing to do. To realize that any fraction where the numerator and denominator are the same number is going to be equal to 1 is useful. And we will be able to use it in so many ways in mathematics that it's worth stopping and looking at it and just appreciating it a little bit. Okay, so I have to do more than one of these. So let's do a few others where we have inverse fractions. How about 2/3 times 3/2? 2 times 3 is 6. 3 times 2 is 6. We have 6/6. Hardest fraction there is to say. And that's equal to 1, which is really easy to say. So whenever we multiply two fractions that are the inverse of each other, we're going to get a numerator and denominator that are the same number, but it's not always going to be 20. So it was 20 here because we had a 5 and a 4 that we were multiplying. Well, it's 6 here because we have a 2 and a 3 we're multiplying. We're not going to be too surprised when this happens. And in fact, it's kind of fun when it happens. It gives us a special case, a bit of variety. I'll do a couple more examples. But we already know what the answers are going to be. If I'm going to do 2 more examples of fraction multiplied by its inverse, you already know the answers are going to be 1. So with that confidence, let's move on and do some. How about 7/8 times 8/7 equals 56/56. Also quite hard to say, which of course is equal to 1. Not to be afraid of. Let's try and make it hard. Should I do one that I'd have to use a calculator for? Okay, I'm going to. I think it might sound scary, but it won't be scary if we realize we know what the answer is going to be. How about 17/19 times 19/17? Well, if I want to show this step, where I have my numerator and denominator the same, we know it's going to happen. That's the part where I might need a calculator. But if I just want to skip ahead to this step, I didn't really need the calculator. I know it's going to happen. That's fun. Here's my calculator. It's very dusty. It's covered with a lot of chalk dust. It's not even on right now. Could I do this in my head? I'm going to try and show off and do it in my head. But then I'll use the calculator to double check. How am I going to multiply 17 by 19? Those numbers are a little large for me to expect to have the answer memorized. So unless I've memorized my multiplication tables way up to 20 times 20, I don't have it memorized. And I'm telling you, I haven't memorized it. So how am I going to find the answer? This is just fun. I'm sort of breaking off into a little fun exercise just to give us a breather from the multiplying of fractions. 17 times 19 is hard to do, but 17 times 20 is not very hard to do. 17 times 20 is the same as if I did 17 times 10 and then did 17 times 10 again and just added them together. 17 times 10 is easy because it's 170. 17 times 10 is also 170. I have to do it twice because I'm not multiplying 17 times 10 right now. I'm just multiplying 17 times 20. So 170 plus 170 is 340. So if it were 17 times 20, I'd have my answer. It would be 340, but it isn't. It's 17 times 19. There's one less than 20 here. It means I need one less 17. So I can say 340 minus 17. And that I might be able to do in my head. 340 minus 17, 340 minus 10 is 330, and 330 minus another 7 is 323. That's my trick to multiply 17 by 19. I multiply 17 by 20 instead, I get an answer, and then I just subtract 17 from it. Do I feel confident in this answer? Yes, I do. I haven't checked it yet. If it's right, if it's correct, that means 19 times 17 will also be 323. So I may as well write this here. I'm so confident that I've gotten it right that I write them both before I check. Why am I confident? Well, one of the reasons is I know that 7 times 9 is 63 because I do know that part of my multiplication tables. So I have that memorized. And 7 times 9 is 63, which ends in 3. Oh, look, these ones end in 3. That's one of the things that helps me feel confident about this. So I think I'm right. Should I check it? Yeah, I'm going to check it. 17 times 19 equals 323. I feel so smart. Okay, now, I'm not making students do 17 times 19 in their heads, but if you can, I'm impressed. And it's a fun thing to practice with, to make yourself feel confident, to realize that you actually don't need a calculator all the time. So yeah, that was a little show-offy, I admit it, but I have an answer. I multiplied two fractions that are inverse of each other, same numerator and denominator, but upside down, and I got an answer that is a fraction with the numerator equal to the denominator, and I know that's equal to 1, so I write equals 1, and I'm done. How am I doing for time? I am still doing good for time. I don't think I have to do any more of examples of these. Which means I've finished my first page, but I accidentally threw away my second page. So I'm going to pick it up. Okay. So I'm good at doing multiplications in my head, but I'm not necessarily good at picking up things from the floor. Okay. Oh, whole numbers. It's amazing how many people get confused by this. And you know I teach adult ed. I teach adults. And sometimes I find myself teaching those adults advanced high school math. And still I find this type of question where you have a whole number instead of a fraction can really confuse people. So I'm going to do a bunch of examples and I'm going to be careful. How about if we have 3/4 times 2? What do we do? Now, those of you who already know the answer are just thinking, okay, well, this is easy. And of course, once you know answers, things do get easy. But what am I going to do? There's more than one way of approaching this. Oh, I wrote a little note to myself and I was trying to read it and understand it. And it's kind of interesting because I'm thinking back to what we did on the previous page. 3/4 times 2 is equal to 3/4 times 2 over 1. I think I'm realizing now that there are some examples I should have done at the beginning. I think I'm going to do some of them. But let's continue. When we're multiplying fractions, we want to have two fractions. But this only gave us one fraction, and the other one was a whole number. What do? I turn the whole number into a fraction, and I can always do that by putting it over a 1. So any number is a fraction as soon as you want it to be, simply by writing the fraction bar and putting a 1 as the denominator. Which means now we have two fractions, and this is no more difficult than the previous examples, the many, many examples we've already done. So 3 times 2 is 6, 4 times 1 is 4, 6/4 is my answer. Hey, the answer has the numerator bigger than the denominator. Why? The fraction I started with had the numerator smaller than the denominator, so why did that happen? Well, because 2 is bigger than 1. So even though I didn't write it as a fraction here so you wouldn't notice it right away, the fraction I ended up using has the numerator bigger than the denominator. And as we've seen from previous examples, when one of the fractions has the numerator bigger than the denominator, sometimes the answer has the numerator bigger than the denominator. So let's do another one. How about 1/6 times 3? I'm writing it nice and big because it's a whole number. But I'm going to convert it into a fraction. So therefore I have 1/6 times 3 over 1. Now I'm writing the 3 small because I needed to make it smaller so that I could fit it into my fraction. And now I'm going to multiply the numerators, and 1 times 3 is 3. And the denominator, 6 times 1 is 6. I have 3/6. Sixths, my favorite word. I actually used to hate that word, but now I'm starting to like it. I think by mentioning how often I find it hard to pronounce, it's making me start to enjoy pronouncing it. Like it's challenging or something. Some things become more fun as they become more challenging. Who would have thought? Okay, 3/6. This time, the numerator is smaller than the denominator. Why? We just multiplied by 2 over 1, where 2 is bigger than 1, and we got an answer where the numerator is bigger than the denominator. But now we multiply by 3 over 1. 3 is even bigger than 1 than 2 is, so why? Oh yeah, oops. You have to look at all the numbers before you will understand when you're going to get a numerator bigger than the denominator or not. So yeah, 3 is a lot bigger than 1, but 1 is a lot smaller than 6. So we ended up with a fraction that has a numerator smaller than the denominator. Multiplying by a whole number, not so bad. Looking at my next notes, I'm trying to remember why I wrote them. That sort of thing has a tendency to happen to teachers. Yeah, doing good for time, so I think I'm ready to move on to some other stuff. I'm going to throw in, though, before I move on to the stuff I have in my notes here, I'm going to throw in something extra that I hadn't really prepared, but I realized we really should have it. Multiplying 3 fractions. Can we do this? Yeah. Do we have to multiply and then get an answer and multiply again? Well, we could do that and it would work. But can we do it all at once? Yeah, we're going to prove it. Why do we have this feeling that we can multiply all this at once? Because we've been in this situation before with simpler multiplications before we had fractions. Like, what if we had 6 times 2 times 5? 6 times 2 is 12, times 5 is 60. So what I did actually was 2 parts. I said 6 times 2 and I got an answer, and then I multiplied it by 5. So I guess I'm not really doing anything different. But the thing is, we don't have to say 6 times 2 is 12 and then say 12 times 5 is 60, because we can say 6 times 2 is 12 times 5 is 60. So really, we can be flexible. We can do it either way. 60 was the answer. There were no fractions here, but since I can do this without fractions, it looks like I can do it with fractions, and I'm going to prove it by doing it. 1 times 2 is 2, times 4 is 8. 2 times 3 is 6, times 5 is 30. It's true. If I tried to do it in pieces, I'll erase the non-fraction multiplication so that I can try doing this again in pieces and feel if I can be sure of my answer. How about 1/2 times 2/3? Ooh. Oh, that's really a messy 3. Okay, I'm going to erase it. Someone's looking at this video saying, what's that thing? What's that thing under that numerator? What's that thing under that fraction bar? Oh, this one's not even that much better. Okay, never mind. 1/2 times 2/3 was the first part of the multiplication. 1 times 2 is 2. 2 times 3 is 6, so I have 2/6. And then I can say 2/6 times 4/5. 2 times 4 is 8. 6 times 5 is 30. Same answer. It worked. Is there another way of showing this? Yes. What if I had 1/2 times 2/3 times 4/5, but I decided to do this part first. 1/2 times, I'm just copying that down because I'm not doing it yet. 2 times 4 is 8. 3 times 5 is 15. Now I'll multiply that answer I got from this part by 1/2. 1 times 8 is 8. 2 times 15 is 30. So many different ways of getting the same answer. Because multiplication is very flexible. When you have multiple multiplications to do, you don't necessarily have to do the one on the left first. It's like that with multiplication and addition, but don't do that with division and subtraction. Slow down and be careful when you're doing division and subtraction. Multiplication and addition are so forgiving when it comes to things like this. But the point of the whole exercise is simply, can we multiply 3 fractions? Yes. We can multiply 3 numbers, so that means we can multiply 3 fractions, because fractions are, of course, numbers. Okay. Erasing. That was fun, though. It's fun to stretch your brain just a little bigger every now and then. And then you go back to the problems where you didn't have to stretch your brain quite so big, and you're saying, oh, this is so easy, this is so easy. That's good. Okay, I needed that. Okay, so my last bunch of notes are kind of on 2 pages at once. So I wanted to remind us of pizzas. Why is he talking about pizza again? Well, where I am, it's almost supper time, so that's probably why. How am I doing for time? I'm doing fine for time. It's to talk about this idea that we kept getting to before, where we got answers that could be reduced, but we weren't reducing them yet. Because now I want to start doing some reducing. Remember these pizzas. So I'm going to draw a large pizza. And whether it's large, small, or medium doesn't really matter. Because when you're doing fractions, it's not about whether it's large or small. It's about how many slices do you cut it into. So this large pizza is cut into 8 slices. Which I've seen a lot. But what if we had a large pizza that was cut into only 2 slices? Starting to look very familiar. It looks very similar to the pizzas that I was talking about with my little story before about half a pizza left in the fridge, and Doug's told by Bunny he can only eat a quarter of the pizza that's left. And okay, so these are both large pizzas. And this one's cut into 8 equal slices, and this is cut into 2 equal slices. So if someone tells me, go up to those pizzas and you can have 1 slice, I can be sneaky and say, okay, I'm going to take one of these really big slices. That's probably what I would do. Now, how about if we have 4 slices left here? So I'll shade in 4 slices. 4 out of 8. Well, that's the fraction I have. 4 out of 8, or 4/8. But then if I go to this other pizza, and I shade in 1 slice, I have 1/2. 1 out of 2, that's 1/2. So we can see that 4/8 of the pizza is equal to 1/2 of a pizza. Remember, both of these pizzas were the same size. They were just cut into different amounts of slices. So 4/8 equals 1/2. That's interesting. And I finally got to the point where I put down this piece of paper, not on the floor. So that means 4/8, this fraction, 4/8, can be simplified to 1/2. So if I get 4/8 as an answer, it means I really also got 1/2 as an answer. I want to give the answer that seems the most simple, because that way the person reading the answer can most easily clearly understand the answer. So this is the idea of simplified answers and simplified fractions. But how can I do that without pizza? So, sadly, still drooling a little bit, still thinking of that opportunity to take a slice this big, I'm going to erase the pizzas, and I'm going to stop talking about pizza. I'm going to leave this thing where we see 4/8 equals 1/2 there because it's still useful to me. How can we simplify 4/8? We can divide both the top and the bottom by something so that we get this. And I'm going to write it like that yet, though. Those two divided by signs, I don't want them yet. And this smudge, I don't want that smudge, I don't want this smudge or this smudge. I'm starting to get fussy. Okay, that's happening because the lesson's getting kind of long. Let me check my time. I don't want to go over an hour. I figure an hour is just about as much pizza as anyone can. Oops. An hour is about as much math as anyone might want to digest at once. Still thinking about the pizza. In fact, if I can be forgiven, let's see, where's my head? Not there. I'm going to put there, there, there. Okay. Does that look okay? And then I'm going to put this thought balloon. I'm going to put the word pizza in it so that you can look at me. And there's Doug thinking about pizza again. So I have to stand right here to really create this illusion, but I'm just going to leave that there because I'm still thinking about pizza. Okay. So the rest of you, stop thinking about pizza. We're thinking about doing this. We want to reduce 4/8 into 1/2. We want to have a way of doing it. So what we're going to do is we're going to divide it by 1. Because we can always divide a number by 1. And the other, it's easy to divide a number by 1. And the other thing that's useful is you know that when you divide a number by 1, you really get the same number. Which is why we usually don't do it. That's a little bit paradoxical. And it's the sort of thing that can be expected from someone whose thoughts aren't always completely on the subject at hand. Okay. We can divide 4/8 by 1. But if I did that, I would just get 4/8. So what I'm going to do instead is I'm going to divide by 1, but I'm not going to divide by this usual version of 1. I'm going to divide it by a clever form of 1. And what am I going to use as my clever form of 1? I'm going to use 4/4. Now remember, from earlier in our lesson, we were thinking about how when you have a fraction where the numerator and the denominator are the same, it's equal to 1. So that means if I want to divide by 4/4, it's okay because I'm just dividing by 1. So I'm always allowed to do that. But the fun thing is when we show the 1 as 4/4, then we can say what's 4 divided by 4, and we get 1. And what's 8 divided by 4, and we get 2. So we have found a way to do this, to show how we know that 4/8 is equal to 1/2. We can divide the top and bottom by the same thing so that we get the most simplified version of the fraction we can find. How do I decide, though, that I used 4? Remember, we've talked about multiples. Multiples are extremely useful when you're working with fractions. It was not the last time I'm going to be talking about multiples. I look at the two numbers I have, the 4 and the 8, and I list their multiples. And I've shown students how to do this before. In fact, the last 2 times I taught some of you, I was showing how to do this. The multiples of 4 always includes 4. The first multiple is always the number itself. And then you double it, and you get 8, and you triple it, and you get 12. You're just saying 4 plus 4, and now we add another 4, now we add another 4. So it's kind of addition, it's kind of multiplication, but it's not very hard. And we just keep on listing them, but we could go on forever, so eventually we have to stop. But I'm doing it backwards. oh no, multiples. I wanted factors. Okay, I don't like that. I'm going to do factors instead. Now, of course, multiples are useful in fractions, and that's why I was starting to do that. But I'm going to do the factors instead, and I did cover that last week as well. So I'm doing it the same way. I'm listing all the factors of 4 and 8, which is a little faster. The factors of 4 start with 1 because factors, any number always has 1 as a factor. And any number always has itself as a factor. And then what are the other factors of 4? The only other one is 2 because 2 times 2 is 4. So I've listed all the factors of 4. Now if I list all the factors of 8, I'm going to put 1 and I'm going to put 8. I'm going to put 2 because 8's an even number, so it has to have 2 as a factor. And I get 4. I have to multiply 2 by 4 to get 8. And then I try 3 and it doesn't work, so I'm finished. 1, 2, 4, 8. I have extra space there I don't need. But then I'm looking for the greatest number that's on both lists, which is the 4. And that's how I knew, it took a long time to say it, but that's how I knew that I could divide this fraction by this clever form of 1, where I chose 4 over 4 because I know 4 is the greatest common factor of 4 and 8. This is why knowing factors is useful before we start fractions. It's one of the reasons it's useful. What if I had tried 2 though? 2 is also a common factor of 4 and 8. I'm going to do some erasing and I'm going to try it again with 2. So I'll erase the factors. What if I wanted to simplify 4 over 8 by dividing it by 1, but I won't show this part, I'm just going to show this part. But instead of showing 4 over 4, what if I had chosen 2 over 2? 4 divided by 2 is 2, 8 divided by 2 is 4. I have 2/4. I'm not wrong. I'm just not finished. Because 2/4 can still be simplified. I can still divide it by 1, a clever form of 1, but I can divide it by 2 over 2. And 2 divided by 2 is 1, and 4 divided by 2 is 2, and I get the same answer. So here I got the answer in 1 step, and here I got the answer in 2 steps. There's nothing to be surprised by this, and in fact, having done it in 2 steps isn't bad, because in the end I got the right answer. I used 2 here, and I used 2 there, and 2 times 2 is 4. This isn't a coincidence. Okay, that was kind of interesting, maybe a little confusing, because the teacher started listing multiples that he didn't actually need. I want to do at least one more example of that. I have a little bit of time left. Where do I put my eraser cloth? Let's reduce another one. Trying to think of the fraction problems I did at the very beginning. I'm trying to remember one of the ones that I didn't bother reducing and say to myself, let's reduce it now. But I can't find them because I made up a bunch of those fractions just out of my head. Let's do one where we got an improper fraction as the answer. 6/5 times 3/2. I'm back to multiplying here because I'm going into the context that we want to reduce a fraction when we get a fraction as an answer to a multiplication, because that's what we're doing right now, an answer that we realize could be simplified further. 6 times 3 is 18, 5 times 2 is 10. This is an improper fraction. This is one of those ones where the numerator is bigger than the denominator, but that doesn't matter. It's a correct answer. We already know it's a correct answer. But can I simplify it? Do 18 and 10 have a common factor? And I think the biggest one I can think of is 2. So I'm going to divide this by 1, which means I'm going to divide it by a clever form of 1, which is 2 over 2. Is this going to fit on my video? Yes, just barely. Okay, so 18 divided by 2 is 9, and 10 divided by 2 is 5. I have 9/5. It is still an improper fraction. It does still have a numerator that's bigger than the denominator, but it has been simplified. It is more simplified than 18/10. So this trick really works, and it works really well, and we can use it a lot. I'll do one more. How about, and I'm just making up a multiplication, start with 10 times 4 over, oops. Trying to put the whole problem inside a fraction. I'll do 10 as my first numerator and 4 as my second numerator. And I'm going to do 12ths and 5ths. There. 10 times 4 equals 40. 12 times 5 equals 60. 40 over 60 is 40 60ths. 60ths is almost as hard for me to pronounce as sixths. But 40 60ths can be reduced. I can divide top and bottom by 10. I can see that because I can see they're both multiples of 10. But I could even find a bigger common factor of 40 and 60. And the one I'm thinking of is 20. I can do it in stages or I can do it all at once. I'm going to divide it by 1. Which means I'm going to divide it by a clever form of 1, which is going to be 20 over 20. I have to pause and give myself a bit more chalk. 40 divided by 20 is 2. 60 divided by 20 is 3. Even this great big fraction, 40 60ths, ends up being able to be simplified quite a lot, and it turns out is equal to 2/3. It works. So these tricks, we use these tricks a lot when we're multiplying fractions, because when you multiply things, things get bigger. And when things get bigger, you're going to end up with big numerators and big denominators, which often can be simplified, so you're going to want to do this. But the take-home lesson of today's lesson is, we are multiplying fractions, we're able to multiply fractions, we are able to do a lot of different types of problem where we multiply fraction. Some of them have weird little complications here and there, but all of them end up being numerator times numerator over denominator times denominator, which is easy. So I'm going to end my lesson now. I'm going to say goodbye for Mocha, who's gone upstairs, so I can't bring her to the camera anymore. I'm going to say, as usual, this has been fun. I look forward to the next lesson where we're going to get into this stuff even more. And I will stand here so that you know, as I finish this lesson, that I'm still thinking about pizza.